With our next session. So I'm jazzed to introduce Pranav and Jonathan from C2FO, which is a financial tech startup in Kansas City, you said?
Yep.
And I don't know about everybody else, I'm real stoked for this talk because I read the abstract and it's about how to make millions of time series predictions. So with that, I'll let Pranav talk.
Cool. First of all, before we get started, I would like to thank the sponsors and organizers of PyData Seattle to make this amazing talk happen. And so I'm Pranav Behel. I'm a data scientist at C2FO. I'm majorly involved there to build the risk management system. And this is Jonathan Stacks. He's a DevOps engineer at C2FO. So today we'll be talking about how to build robust automated forecasting system in Python and R. Before I dive into the techniques that we can implement on time series data, just to give you an overview for those who don't know what time series data is. So it's a series of data points indexed in chronological order with an equal time space in between. So let's suppose if you're dealing with data, daily data, then we have observation for every day. So in time series, we have time or date as the independent variable and the values as the dependent variable. So I have this fictitious data that I use to represent how time series data actually look like. On the x-axis, I have the time. On the y-axis, I have amount, just showing a fictitious data for the financial transactions. So the blue represents the actual time series data, whereas red represents the forecasted value, which we can get once we build the forecasting models. So let's get started. So the goal of this talk is to demonstrate how we can make millions of robust forecasts in an automated fashion. So first I'll be defining the problem, and then I'll walk you through some of the pre-processing steps that we can implement for time series data, which involves profiling the data, applying different kind of transformations on the time series data, and then detecting for outliers or anomalies. Once we know how to pre-process the data, I'll walk you through some of the strategies that we can apply on time series data. And the packages that we'll be using are from Python and R. And then to calculate the forecast quality of the forecasting model that we'll be implementing, I'll walk you through some of the evaluation metrics that we can use to calculate that. And then once we have our software architecture built up, I'll be walking you through how we can choose the best hardware for a given use case, or in this case, it'll be the problem statement that we are solving. So the forecasting that we do on daily basis is used throughout our underwriting process. And because of the problem statement that we are trying to solve, we are biased towards the risk aversion. And on daily basis, we do the prediction for more than 250,000 unique time series, or we call them as accounts. And the data grows at the pace of around 2x every year. So the initial goal we had was to keep the runtime of complete pipeline under 5 hours, at the same time optimizing for the cost and keeping it under $200 per day. And the aim of doing all this is to reduce the forecast error by 10% compared to the current pipeline. So, and these are some of the simple formulas that we use to estimate the runtime and cost for every pipeline run. So these are used to tweak some of the variables that we have. In our case, right now we have the number of servers as the main variable. So if we want to reduce the runtime, we can bump up the number of servers we'll be running our pipeline on. So to calculate the runtime on numerator, we have number of unique accounts or number of unique time series we'll be forecasting for, multiplied by the number of strategies we'll be running, multiply that by the number of transformations that we'll be applying on the time series data, and divide that by the number of servers we'll be running our complete pipeline on, multiplied by the cores each server has into the mean forecasting time per unique time series. And once we have the runtime calculated, we can easily calculate the cost, in which we just multiply runtime with the number of servers we are running our pipeline on, multiplied by the cost per server. So now let's see what different steps we can perform to pre-process the time series data. The very first step that we can do is to profile the data, in which we make sure that the index of the time series data is of type timestamp, and then we check for the completeness of panel, by which I mean, let's suppose if you're dealing with the financial data, we don't actually see transactions every day. So to fill on those days where we don't see transactions, we just fill the null values. And one of the most important thing to take care of if you're dealing with the daily data, because the frequency for daily data is 365, so just remove the leap days. And if you're dealing with the time series data which has seasonality, so make sure before doing any kind of forecasting, your data has at least one complete season. And also, make sure that you truncate any incomplete season from your data. So to demonstrate that, as you can see in this graph, so first of all, red reflects the original time series that we had, and blue reflects the profile time series. So as you can see, there's some data after 2017. If, let's suppose, we are dealing with the daily data, doesn't seem like that it's a complete season. So we try to get rid of that extra data. But rather than getting rid of that data from the recent history, we just get rid of the data from the past, because recent observations are more useful to make future predictions. And then other step that we can perform under pre-processing is imputing the missing values. So one of the simplest way that we can do by filling the missing values is using descriptive statistics like mean or median to replace the missing values. The other strategy or technique that we have is called interpolation. So if you look at the very first graph, we have a disconnection in the time series which reflects the missing data. So idea behind interpolation is to take the coordinates where we see there's a disconnection in the time series and apply different techniques like linear polynomial or cubic, and then replace the missing data accordingly, as we can see in the second graph. Whereas extrapolation is a technique which we use when the missing data is at the very end of the time series, as opposed to what we see in the interpolation. And the strategy we can use in extrapolation is forecast a training model or forecasting model on the time series data, and then make predictions for the missing values in time series. The other thing that we can do is detect for outliers or anomalies. So just to give you a brief how they are different. So outlier is a data point or a bunch of data point that lies farther away from a statistical mean or median of your data distribution. And some of the common ways to look for outlier is plot box plot, or you can decompose the time series into different components like trends, seasonality, and residuals, and work on the individual component to look for outliers. Whereas anomaly is an illegitimate data point in the data distribution that you have. By that I mean, let's suppose if you're dealing with the weather data, and then you are looking for a weather data for a city which experiences hot summers, and you're looking at the summer data itself, and then you experience or you see an observation which is pretty low, like 40 Fahrenheit, which looks like an anomaly. So one of the common way to detect the anomaly is to divide your time series data into trained data and holdout set, and then build a forecasting model on the trained data and calculate the forecast error for the holdout set. And once you have the forecast error, you can compare that to the threshold through which you can detect if a data point in the time series is anomaly or not, and that threshold is again dependent on the use case or the type of data that you're dealing with. So yeah, this is one of the interesting examples that I wanted to bring up. So this is a fictitious data that I'm using. So one of the ways we can detect or remove outliers is just, if you can see in the first graph, the data looks pretty stationary. So the technique we are using is like any data point which is beyond second standard deviation, we just get rid of that. that looks like working fine in the very first graph because we have a stationary data. But if you try to imply the same thing for a data in which we have moving mean and moving standard deviation, that doesn't seem like working as we expected, because it seems like we are getting rid of some of the legitimate data points here. So just keep in mind if you're dealing with data with trends or moving means. So this is not the technique to use for outlier detection. So now, as we know how we can pre-process the data, let's look at some of the forecasting models or strategies, different type of strategies that we can implement on time series data. So one of the strategies, which is pretty common, is using regression models. So in regression models, we can build models like OLS, polynomial. But the problem with the regression model is, like, if you're using just the univariate time series data, trend not always follows the parametric behavior. And even if it does, you will end up with residuals with high correlation. But you can use regression if you extract features out of time series, and then you can build up some of the complex regression model like XGBoost. Then we have other models called ARMA, known as autoregressive moving averages. So ARMA and smoothing models share a lot of common characteristics. So first of all, they are based on the idea like tomorrow's prediction is based on today's data and some of the recent past data. And also, they are mostly used when you're dealing with just a univariate time series. But the only difference, or the major difference, is some of the smoothing strategies can also be used for nonlinear data, whereas ARMA is basically used for the situation where you're just dealing with the univariate time series. And then we have structural models, also known as state space models. So the idea behind these models or type of strategies is tomorrow's prediction is basically dependent on today's state only. And the idea behind using these models is when you are dealing, or when the time series data observation value is not just dependent on the time, but also some of the other factors, like in stock market, there's no price over the weekend. So now we know how to build different forecasting models on the time series. So let's see how we can evaluate the forecasting quality that we get out of those strategies. So there are two different types of evaluation metrics. One is scale dependent, which requires that two time series models that you're comparing, or two time series that you're actually comparing, should be on the same scale. Like, you can't use a time series which has observation in kilograms and other in grams. So some of the common examples for scale dependent are mean absolute error, where we take the mean of forecast error. And forecast error is just the difference between the forecasted value and the actual value. And some other examples are mean squared error, mean forecast error, and root mean squared errors. So whereas scale dependent, which is other type of evaluation metric, this is used when you have time series, two time series that you're comparing on a different scale. So we can use scale independent just because, so most of the examples for scale independent are percentage errors. So here we care about by how much percentage are we away from the actuals. So as you can see, in mean percentage error, we are dividing the forecast by the actual values and then multiplying the mean of that to the 100 to get the percentage. So other example is mean absolute scaled error. So this is actually based on the idea to see your forecasting model is how far from the naive model, in which today's prediction is solely dependent on what is yesterday's observation value was. And now we know how to perform different steps and build forecasts. Let's see how we utilize all that information for our problem statement. So our problem statement is divided into two sub-goals. One was runtime optimization, in which we'll try to narrow down different strategies and transformations that we can apply on the time series data. And then other goal that we have is cost optimization, in which we'll try to use different options for the hardwares to reduce the costs for each pipeline run. So let's see how we optimize for the runtime. So this is the graph to show what was our initial approach. Our initial approach was to implement different strategies that we can on our time series data, and then also apply different transformation. For initially, we just used log transformation, and default here reflects a data without any transformation. And to measure the forecasting quality, we went ahead and used a bunch of different metrics because we had no idea and we wanted to get a feel how or what kind of result they output, and if they fall in consensus, we might just use all of them. And then once we have that, we implemented all of that software part in Python version 2 as well as Python version 3. So as I said, we wanted to build a robust forecasting system, so we wanted to see which Python version is performing the best for our use case. And then once we have the software part figured out, we'll see which hardware instance order type is best for our problem statement. So the very first experiment that we performed, or before I get into the experiment, so we used 1,000 different unique time series or 1,000 accounts. And those 1,000 of accounts or unique time series reflect the diversity of the data that we deal with on daily basis. So we did all the experiment on those 1,000 accounts. And yeah, so the first experiment was to get the feel of metrics and see if all of the metrics fall in consensus. And so if so, then use all of it. Otherwise, try to get rid of some of the metrics which are throwing away redundant information, or if they have any kind of conflicts. So let's see. Okay, before you get overwhelmed with this graph, let me explain you what this graph is used for. So this graph is to compare all the different strategies that I mentioned in last slide. So we are running all the different strategies with the different transformations, and we are comparing their results across different metrics, which are labeled on the x-axis. On the y-axis, I have the number of win counts or number of accounts for which a particular strategy and transformation combination won. So if you look at, there's a continuous line and a dotted line with the same color. So continuous line reflects a strategy built on the default data, which is non-transformed data, and dotted reflects the same strategy built on the log transformed data. So just to give you an example, if you look at the dotted line, the orange dotted line under MPE, which is the very first metric, the count seems to be around 125. So what it says is, like, out of all 1,000 accounts, we experimented, so that dotted orange reflects plog autorema. So Python autorema ran with the log transformation. So that is winning 125 times out of 1,000 unique time series that we experimented. So in this graph, I try to bunch all the different metrics which have same characteristic together. So if you see on the left, so left to the MASE, which is kind of in the middle, is the scale independent metrics, and everything towards the right of MASE is scale dependent metrics. So if you look closely, there's a huge conflict between the percentage error metrics, which are first three, compared to any other metrics that we have. And this calls out for the situation where we should not be using percentage errors, which was our problem statement. So in our problem statement, in our actuals or test data or holdout set, we had zeros. And if you remember, in percentage error, we divide forecast error by the actual values. So if you divide something by 0, it'll just give you error. But to just get rid of that, we added a small constant, but that still didn't seem to be solving the problem. So we thought of getting rid of all the percentage errors because either ways we are dealing with all the time series on the same scale. And then the other thing that we looked for, if you look at MSE, RMSE, and SSE towards the right side, so we can see they are showing some of the redundant results. So we thought of keeping just one metric and getting rid of other two. So similarly, we went ahead and got rid of anything which is marked in the red block. So ultimately, we were left with MFE, RMSE, SMAP, and MACE. So now we know what metrics are useful for us. So let's see what else we can do for optimizing the time. So the next experiment that we ran was to get a feel how our different strategies are performing. So let's see how they are performing. And one more thing that we wanted to look in this experiment was to try different parameter values for different strategies that we are implementing. But initially, we started off with the default parameters, except for PyFlux, one of the strategies that we are using. We used a reduced number of simulations for that. So again, this is kind of the graph that we had in last experiment. On the x-axis, I have metric. On the y, I have number of win counts. So the purple one, which is at the very top, reflects our autorema with default transformation, which means no transformation. That is winning over, or that is winning followed by TBATS, followed by Python autorema, followed by Profit. So those seems to be performing really good for our unique time series that we have. But then if we look at the very bottom, so every color or every line associated with PyFlux seem to be lying at the very bottom, which means PyFlux is not actually performing good for our use case or our problem statement. So analyzing that, we thought of getting rid of PyFlux from our strategies. And just because, so the most time-consuming thing in this whole architecture is strategies. So we wanted to see if we can do something more to get or reduce the time. So I forgot to mention one thing earlier. So PyArema is nothing but the implementation of our autorema in Python. So this is a homegrown algorithm. So we wrote it according to our problem statement. So the idea is, because if you remember the last graph, our autorema was performing the best out of all the strategies. So the idea here is to get rid of Python implementation of ours autorema if the difference between the forecasts of Python autorema and our autorema is not too much. So we looked at the cases where only Python autorema was winning, and we wanted to see how our autorema is far away from Python autorema forecasts. So we went ahead and looked at the median of differences. And we calculated differences amongst all the different metrics, but here I'm just showing MFE and RMSE. And so the values that you can see here for MFE for the default transformation or no transformation was 1367. Similarly, for log transformation was 3731. For our use case, it was under our expected limit. So we went ahead and got rid of Python autorema. Now we have our strategies figured out. So we went on to transformations and added, researched a bit and added one more transformation, which was Box-Cox transformation. And then another experiment that we performed was to figure out which Python version is performing the best for our use case. And to do that, what we did was we ran combination of all strategies, transformation, and different hardware we want to experiment. And there were total of 45 combinations we came up with. We wanted to compare the timing of Python version 2 to the Python version 3. I know it's a bit confusing, this graph. The only thing that we have to care about is the red reflects the Python version 2 processing time, whereas blue reflects the Python version 3 processing time. And in most of the cases, if you just overlook, we can see red is the value for red is higher, which reflects Python version 2 is taking more time compared to Python version 3. And to summarize this graph, I compared the timings against different calculation types. One was pre-processing, how it is performing, or how different versions are performing for pre-processing, and then modeling, which was the main part, and then at the last, comparing the cumulative times. So as we can see, Python version 3 seems to be a clear winner here. So we went ahead and got rid of Python 2 and declared Python 3 as our version for new pipeline. And now let's see how we can decide what hardware works the best for us. We already ran all the different combinations, and we already had the timing for all of them. So we just compared the timing across different hardware types that we want our pipeline to be running on, or different hardwares that were available. And we compared the time, as we can see. So the very first here is C48 type, so which is a compute optimized hardware instance. So, and that makes sense because we are doing a lot of modeling, which is compute heavy. So C48 seems to be a clear winner here. So we went ahead and got rid of other hardware types, and we decided to run our pipeline on the compute optimized system. And then we had everything figured out, except that we just wanted to optimize some of our runtime more if we can. Then we had two questions. One was, is there any strategy which is taking longer time compared to other strategies? And also, to run some of the R code, we are using RPy2. So is that creating any kind of an overhead in our code? And we can just replace that with something more optimized. So for the very first, we compared the timing for all the different models that we are running. So the three bars that you can see in the center reflects the R auto-REMA strategy running on three different transformations. And we can see R auto-REMA is taking comparatively very high time compared to other strategies. So we went ahead and looked closely at the stats. So just forget about auto-REMA for a minute and look at TBATS and profit. So we can see the mean forecasting time for TBATS, all the timings are in seconds, is just 5 seconds. For profit, the mean is around just 3 seconds. And the max for TBATS is 31, and profit is just 5 seconds. But now, if we look at auto-REMA, the mean is 33 seconds, which is pretty high compared to other two models. And also, if you look at mean and then look at the 75th percentile, which is 24 seconds, whereas mean is 33 seconds, which signifies there's something going wrong, or there are some accounts which are taking really huge amount of time to process. And even if you look at the max, one of the account was taking 1600 seconds, which is a little lesser than half an hour. So then we looked at the distribution of the data under second standard deviation. And we see, just for the auto-REMA, if you look at, the mean became half of what we had for all the samples. It is 19 seconds now, and the max is just 232 seconds. Looking at this, we came to a position where we thought we'll be implying a time threshold of 5 minutes, which is 300 seconds. And we'll just time out anything which is taking more than 5 minutes. And before we would have went ahead doing that, we thought of analyzing how much forecasting strength will we be losing if we do that. So out of all the 1,000 accounts, there were 26 accounts or 26 unique time series which would have timed out in case of auto-REMA. But out of those 26, there are only 14 unique time series or accounts which have R auto-REMA as the winning strategy. And as we can see, this graph reflects how many times out of those 26 with strategies winning how much. So R auto-REMA with no transformation is winning the most with 7 count. So then the idea was to look at the difference distribution, by which I mean let's suppose for an account, our autorema or profit is the winning strategy. Compare that to what is the next winning strategy. What is the difference between them? So we plotted that on the left-hand side, as you can see, and compared that to the MFE, or we're just keeping evaluation metric as MFE here. So we compared the difference distribution for the cases where our autorema was exceeding 300 seconds, but was winning for those accounts. So if you remember, there were 7 accounts for our autorema with no transformation. So I'm just looking just for the visualization purpose here, I'm just showing only that case. So as we can see, for more than half of the accounts, which is 4 accounts, the difference is pretty low, though we have some of the outliers. So based on that, we thought of moving ahead and implementing 300 seconds or 5 minutes as our time threshold. So this helped us to gain 10% of speed up with a maintainable, acceptable loss that we can have in forecasting strength. And then the other problem that I mentioned we had was RPy2 that could have caused overhead. But before we could have went ahead and analyzed how much overhead RPy2 is causing, we went into a problem when we were applying for the time threshold. RPy2 was not efficient to apply time threshold. It was not able to time out at a given time. So the only solution, or the solution that we came up with after to get rid of RPy2 was to build individual scripts for all the R codes and call them from Python subprocess. And then after that, we figured one more strategy out, which was Bayesian structural time series. It's kind of a state space model. We wanted to add that, and before adding that, we again experimented and see how it was performing. So yellow line reflects our Bayesian structural time series, and it was performing considerably good, especially if we compare that to PyFlux, which we saw was performing very poorly for our use case. So then we went ahead and kept BSTS as one of our strategy. And this is what became our concluding pipeline. And then second part is optimizing for the scale and cost, which will be covered by Jonathan Stacks.
Thank you, Pranav. I'm going to talk real briefly on scale and cost optimization. So now that we had our forecast on what we were going to run, we needed a way to scale it up. So the first thing we looked at using is Docker. We'd already been using this pretty widely at C2FO. There's a lot of tools around deploying it, and that we had a deployment system already tailored around this. So from a show of hands, how many people have heard of or used Docker? Okay, great. I think for the scientific Python community, it could be a great fit. If you're using Conda, it's really easy to install your Conda environment into a Docker image. The other benefit of this is when you go to deploy across the cluster, you don't have to rebuild on every single machine. You can take that immutable image and you can just directly drop it on and then spin up as many containers as you need. And then one final point, you can run the same code in production that you do on your local machine, so developers can develop and there's no more throwing it over the wall and saying, well, it worked on my machine, I don't know why it's not working in production. So this is the basic architecture of our pipeline. The piece that we were breaking out and optimizing was this piece right here where we're using Celery to spin up a bunch of Docker workers on ECS. We're pulling data out of Redshift into a temporary database, and then all these workers are consuming it, doing the forecast, and then we're writing results up to S3. And then those are going, like I said, it's Apache Parquet. And like we mentioned earlier, we're running Docker on the C4 8x large instances, and our main pipeline is in Luigi. So this is a better look at the concurrency implementation. So initially, we prime our database with data that we pull out of Redshift. It's not really efficient to keep hitting it with lots of workers when you're running lots of forecast. So we do that initial load once. And then in ECS, we spin up 1,000 workers right now that are all processing data. We're using Celery, so we load the messages onto the queue. Each worker picks up a message, says, hey, I'm supposed to process this account, goes to the database, gets the data, starts churning it, and then writes the forecast up to S3. And then we're using Redis as a backend for Celery, so it's writing all the task info and state there, so we can monitor them with Flower, if anyone's ever heard of that, or Flower, I think some people pronounce it. So this is the basic implementation that we have. Some stats that we have, we're running this across 28 instances, since each one is 36 cores. That gives us 1,008 cores when we run 1,000 workers. We do about 2.6 million forecasts in around 5.5 hours. The 0.5 hours is mainly for cluster spin up time. The whole pipeline runs in about 5 hours though. One thing that I really wanted to drive home here was if you have the opportunity to use spot instances, it requires a little bit more configuration on your part in the fact that you don't know when that instance is going to go away. So you need to make sure that you're writing robust infrastructure and code. But the cost is quite a reduction. So the thing is too is that you can lose them at any time because it's based on a bidding model. So if a lot of people want to run spot instances, the price goes up. So you just have to be aware of that. But the cost per run is about, I think, 40%. So if you can, and you can write your architecture around that, I would say use spot instances. So in conclusion, implementing all of this resulted in a reduction of forecasting error. As you can see, this is on log scale, but we've shifted down the percent difference. So Pranav, do you want to come back up?
Hello. Yeah, some of the future improvements that we are thinking of is running the experiment on schedule basis so that if any of the libraries gets upgrades, we can look for that, because one of the significant changes that we figured out was in the case of FB Profit, they upgraded their library and there was a significant change in the results. And then add some of the regression models or the XGBoost that I was talking. So we are working on that to extract the feature from time series and add some of the regression models, and then investigate if we can move from Amazon to Google, and if that performs better.
We were also looking at AWS Batch there. That would really help decouple us from our data science team and allow them to kind of self-service their own jobs. In addition, AWS Batch also will spin up and down workloads, resulting in cost savings as well. So that was an exciting new product that we want to look into.
So these are some of the references that you can look for if you want to know some of the more details about the forecasting, pre-processing, or even to know more about C2FO. So any questions? Yeah.
Are you using Parquet storage? Because you're doing post-processing, why did you choose that?
So Parquet is something that.
Just make sure to repeat the question.
Okay, so the question was, why are we using Parquet? So Parquet is actually something that we are thinking of using down the line, so that rather than extracting all the data into a temporary SQL for which we pay, or database for which we pay, if we can get all of the data in a flattened file, and it'll be more accessible. Any other questions?
I've got one.
Okay.
So I'm curious, you talked about sort of, clearly there was like this part at the beginning where you're like, kind of splashing around and like trying this out, and then like, at the end you have this like clean, like we've got Docker, we've got, everything running, we can deploy it on EC2. Mm-hmm. Like a common thing that I see people spend a lot of time beating their head against is sort of like, what are the smooth paths or the things that work particularly well or poorly from like, you have some people basically just wanting to write a little bit of Python or R to like, DevOps has something in their hands and there's a smooth path to deploying that. Like, are there any other thoughts or, lessons learned that you might want to offer from that part of the story?
I'll take the first part. From our talk, it kind of seemed like a handoff in the middle, but we were definitely involved early on. We were working through the same instance types and running forecast all the time. Early on, to even run our forecast in an automated way and allow Pranav to do these different experiments, we actually automated that. So he could go in and he would push up a branch of code that maybe tweak something, and then he could go through our automated deployment system. He could just hit deploy, and then the results were posted up in S3. He could pull them down, analyze them from any number of instances. So that was kind of something that we worked on continuously. And I would say it definitely behooves anyone to involve DevOps or even like infrastructure ops teams earlier than later, because so they can work with you and they can know what's going on. I think that helps.
Okay. All right, sorry, my phone call mid question check was poorly timed.
Yep.
I've just got one here. After you ran all of your experiments, it seemed like you still had 4 candidate models left. What does that look like in practice? Like when you get something that you need to forecast, do you pick one of them?
Yeah, so the question is if you're running different strategies, how you're picking up the models, right?
Sorry, I thought you were trying to distill it down into one final model that
No.
uses your pipeline.
So the thing is, what we figured out why we are using different strategies, because there are some properties different amongst all the different strategies, and all of the time series data that we have doesn't reflect the same characteristics. So in some cases, we have a lot of days where we don't see any transactions. So there are some of models that picks up that thing very well, whereas there are some models which picks up the heavy data very well, where we have the transactions throughout our time span. So there are different times of time series that we are dealing with, and just because of that, there are different characteristics each strategy have, and they pick on that.
So we run them all, and then we choose the best one at the end.
Yeah, yeah.
So that's why we're running so many forecasts.
Yeah, so as I mentioned, different evaluation metrics that we are using. So finally, we came, right now we are working on having a meta metric, and we have combined MFE and RMSE together. So combined sum, so any strategy which has lower combined sum wins for a particular unique time series or an account.
Sorry,
Yeah.
I think I'm misunderstanding. Why do you use multiple different evaluation metrics?
So initially, the idea was to use different evaluation metrics if they are in consensus, and keep all of them and try to build up a meta metrics, which we can use to compare different strategies and pick up the best model using that. Yeah.
All right, I think we're good. So let's thank our speakers again. And if you're watching on the live stream, we'll be back in just a minute with the next talk.